Kristen Atchison here, and we are still talking about the sound in the ear. We are on our third video lecture talking about the neural representation. So we said that the basilar membrane is vibrating and that's sending information into the organ of corti. When we talked about the ear, we talked about the sound waves and how those different perceptions of those, the perceptual dimensions and the physical dimensions. Now we're going to kind of pull all that stuff together and we're going to talk about the different ways that it's being transduced into the auditory nerve. So again, human hearing is about 15 to 20 hertz up to about 20,000 hertz. Again, you saw this on that video, that YouTube video about the human hearing range. There's two different ways that we discuss that this frequency information is being transduced. One way we're saying it's done is the place theory, and it's saying that place codes, it's about where on the basilar membrane the sounds are being hit. Remember, it's sensitive to different frequencies in different places, and this really works above 5,000 hertz. So above 5,000 hertz, this is where this is primarily doing its best work. It works a little bit lower, but it does its best work above 5,000 hertz. The temporal code is saying that it's giving information about the literal frequency of those waves. And so basically, as there's higher frequency, you have a higher fire rate. So it's about the timing of that. Remember, hertz is number of cycles per second. So the more cycles per second you have, the higher the firing rate of this thing. And this is talked about in the temporal code. And this works best at the lower end of our frequency range from about 20 hertz to about 5,000 hertz. So in terms of the place theory, this refers to where the displacement of the membrane is most pronounced. So this is what piece of the basilar membrane is being affected. Again, it's really working best above 5,000 hertz. And this information is called the place code. So in terms of the cochlea and the basilar membrane, here we have the cochlea all curled up. Here we have the cochlea all stretched out. And again, basically what we're saying is where the basilar membrane vibrates is what's sending the information. So at a high frequency, the basilar membrane would tell us, oh, it's happening at the beginning of this basilar membrane, so that's a high frequency, versus it's happening at the end of this basilar membrane, that's a low frequency. And again, this information is being transduced, these little cilia, you can see these little black dots are being moved, and that's transducing this into the nerve signals. Where the frequency theory says that the neuron's firing rate matches the hertz, the cycles per second. But this really only works with those lower frequency sounds, about 20 to 4,000 or 5,000 hertz. And this is called the temporal code. So the same thing's happening in terms of the cochlea and the basilar membrane, but it's saying how it vibrates is the difference. So where in the place theory, we talked about where it was happening is happening at the top versus the bottom. We were talking about the location that this was happening. The temporal code, we're talking about the actual how it's vibrating. So the blue line is vibrating with a higher frequency than the blue line is, the red line is vibrating. And there's also differences in amplitude as well, but the red line has a higher the blue line has a higher frequency. We have more cycles per second there than we have on the red line. And the temporal code is going to be using that information. So now let's talk about some evidence for these two kinds of theories, and we'll talk about each of these in more detail. So the place code for frequency was first talked about by von Helmholtz. We've talked about him already. He really established this physical basis. Because the basilar membrane has different thicknesses and different stiffness, it responds to different sounds in different ways. And he was, again, the first to really determine that this displacement was happening in the inner ear. Or von Besky actually measured this membrane movement using a microscope and strobe light. So he was able to kind of physically see, oh, this thing is moving, and make these connections. One of the ways that we see this support is through the physiological frequency turning curves, okay? And what this is it's about the frequency tuning of a neuron. It can be almost entirely accounted for about where it's being vibrated. So if you look at these two lines, so we have the blue line and the red line. This stimulus was at the 9,500 hertz, okay? And they are absolutely identical. You can't even see the blue line anymore because the red line is so on top of it. And so again, it's giving us the exact same information, this purely physiological, where it's being moved is affecting this firing rate. We see this, again, they're straight on top of each other. And again, we're really better at this with the high frequency sounds and the low frequency sounds. So down here, we're not going to see before 5,000 hertz. You can see that those lines are further apart. They're close, their shape is similar, but they're further apart. Whereas once we get past 5,000 hertz, they pretty much get straight on top of each other. And again, are firing in very, very similar ways. And so again, this is support for that where the basilar membrane is being affected is corresponding to that neural information, at least above 5,000 hertz. Another example is this, again, the place codes better at the high frequencies than the lower frequencies. Again, the more narrow these curves are, the more they look like a V, the thinner those two lines get together is about accuracy. And we see that where the pink one starts is where we really start getting much better accuracy, and that's, again, about 5,000 hertz, right there. But notice that the place is still matters before 5,000 hertz. So there is some overlap between this place and temporal codes between about 500 and 5,000 hertz. This is really good news that we're getting information from both the place where on the basilar membrane it's happening and the how it's vibrating on the temporal code, that we're getting overlap of information, because that's the range of human speech. So that's going to be really, really important to us in terms of being able to understand what people are saying and being able to really have good information, this overlapping information. And so again, we're seeing this overlap between about 500 and 5,000 hertz. So one of the other ways that we support this place code theory is through the psychophysical frequency of tuning curves, okay? So the way they do this is they present someone with a noise masker. It's like white noise. So you know that static on the radio is white noise. But they're able to kind of tune that white noise into a particular frequency range. Then they also present a target tone. This is going to be a pure tone, and it's going to be where they're interested in saying, okay, this is what we're trying to activate. This is what we're trying to get you to listen to. And again, they can make this masking noise, this white noise, the center of it match that target tone. So if we're having a target tone of 200 hertz or 2,000 hertz, they can make that white noise mask it around the same range. The masker is going to activate the auditory nerve because it has all of that information in it. White noise is a mixture of all these different noises together, all these different hertz together. But when they center it around a specific, they kind of average it around a specific one. What they'll see is that the masker only has to be a little bit louder than the target tone when these frequencies match. So it can be, it has to be a lot louder. So this is basically, can you hear this tone? Okay. And when the white noise doesn't match that tone, it has to be pretty loud for it to really mask it, that white noise to block out this tone that you're listening to, okay? But when they match that range, they have that average frequency for the white noise match that tone, it only has to be a little bit louder because again, it's activating that same neuron quicker, that same information quicker when they matches. So again, this also, if you look at these turning curves, they're very, very similar. Tuning curves are very, very similar to the physiological turning curves. So again, we have this similarity between the two is again indicative that there really is support for where the basilar membrane is responding as to our corresponding information about pitch. and from frequency. So we talked about place code. Now we're going to talk about temporal code. Again, there is some overlap between about 500 hertz and 5,000 hertz, but we see that, again, the temporal information is doing best below 5,000 hertz, and the place code is doing best above 5,000 hertz. So the frequency theory is, again, it's saying that the frequencies coming in match the firing rates of those auditory neurons, those nerve fibers, okay? And this is called phase synchronization. So here on this image here, what we see is the sound wave, the red, and you can see that they've marked the peak of this. They've marked kind of each, the peak of each one of them here. So the kind of the loudest, the frequency of it. And what's interesting is if you look at the neuron fibers, where they're spiking is at these peaks. So follow these dotted lines down. This is those peaks, and we'll see that those are matching that information. Now, it's not doing it all in just one. It's doing a bunch of different nerve fibers are doing this because, again, it's going to be multiple nerves are going to be activated. But the problem with this is the reason it's going to limit at about 4,000 to 5,000 hertz is because neurons can only fire so fast. So once we get above about 5,000 hertz, the neurons can't fire fast enough to really match this frequency. Because those curves get closer and closer together, they can't fire that quickly, and so we lose that information. So place code is going to be best above 5,000 hertz. It's going to make up for the fact that the temporal code can't fire that fast. And so then the place theory really can take over. The place code can really take over. Whereas below 5,000 hertz, the neurons can fire quick enough to mirror this, to really match this. And so we'll see that the temporal code is going to be most important below there. Again, we have that overlap between place and temporal between about 500 and 5,000 so that we're getting some similar information about frequencies from two different avenues, which again is really advantageous for us. So we talked about frequency. How does amplitude factor into this? So amplitude generally goes up, and as amplitude goes up, so does firing rate, generally. But the problem is that this doesn't happen in a straight line. Of course it doesn't. That'd be too easy, right? And this is because there's a range for each auditory fiber about when it fires best. Think back to receptive fields. It fired best in these certain areas, in these certain situations. It's going to be similar to that. So dynamic range is the range of amplitudes that can be heard and discriminated, and this neuron will really change its firing rate in response to that. So if you look at this graph, where it's changing, where it's not flatlining, is this dynamic range. There's a change there. Before that, we're at this baseline firing rate. When we pass that threshold, that's when we're into this dynamic range. But then we get to a point where it's just too much and the neuron can't do it anymore. And that's when we hit saturation level. So neurons are really sensitive to particular frequencies. And so they'll fire at a lower amplitude for that frequency than others. So you can see that here. So one way, again, the higher the rate of the higher the amplitude, the louder the sound. So we'll have a higher firing rate with a loud sound. The other way, again, is that specific neurons are going to do better in certain situations. They're going to be sensitive to certain frequencies. So you see here these different neurons that are sensitive to different frequencies. And you can see down like this green one, it will fire at a lot lower auditory threshold, a lot lower decibel for its preferred frequency. It fires, period. Doesn't matter the decibel for these other frequencies, but it can do this one frequency a lot better, and it's a lot more sensitive to that one frequency. So these are all firing. It's just there's different sensitivities, and so this will give us information about both frequency and amplitude. So both of these things. So the other way we can do it is the more neurons are firing, the louder the sound is, okay? So here, at about 90 hertz, everybody's firing. Not a problem, doesn't matter, especially in that range of 500 to 5,000 hertz. they're all firing, right? But we see that they can fire with more sensitivity when it's a frequency that they're sensitive to. So again, different auditory nerve fibers have different thresholds and different dynamic ranges. So here's that same graph just blown up so you can see it better. Again, we're only seeing that change happening, that firing rate change happening in this dynamic range. When it flatlines, when it's at the baseline at the beginning, that is before it hits that threshold. And when it flatlines at the end, it's just kind of done. It's hit a saturation level. It's not going to change anymore. It's still firing, but the change of firing rate's not going to change even with increased amplitude. So it doesn't matter if you turn it up anymore, turn the volume up anymore, we've hit a saturation level. It's not going to increase its firing. And again, the brain can use these different patterns to gauge amplitude too, because different neurons will have different responses to different dynamic ranges, to different amplitudes. This can also be used to give us information about the loudness of the sound too. Just as we use different information to get the frequencies of the sound, we can use different information to get the loudness of the sound too. So this ends our discussion about the neural representation of frequency and amplitude and our discussion about chapter 9. Thanks.